All right. Hello, everyone, and thank you for joining GEWEX Global Flood Crosscutting Project monthly meeting. Before we start with our awesome keynote speaker, I would like to share a few points with you all. First of all, as you know, we continue this monthly meeting, hopefully till the end of this year, and after that we start working on a report for GEWEX Global Hydrology Panel. And then I would invite each of you to please stay and join us in that moment as well to shape the report. And to do so, we created a Google Doc where you can actually, let me find the chat box. You can add your research related to flooding here. If you publish your work or provided any kind of great discussion and great finding in related to flooding in your case study in your particular region, we would be happy to include those results in the final report. So please add your papers and publication to this Google Doc so that we can use it while we shaping the final report. As you guys know, every month we have well-known keynote speaker in our monthly meeting. And this month, we are honored to have Professor Hayley Fowler as our keynote speaker. She's well known to all of us, so a formal introduction is hardly necessary here. Hayley, thank you for accepting our invitation and for joining us today. The floor is yours. If you could check your system and see, would you be able to share your screen before you get started? Great. You're muted, Hayley, if you're...
Yeah, I was just trying to work out how to sort that out, but I think I have. Right, can you hear me? Yeah?
Yeah.
Excellent. Right, good. All right. Thanks for all coming. I'm gonna give talk about what I understand to be happening about extreme weather, particularly concentrating on extreme rainstorms and floods, since that's what we're all interested in here. What's happening now and what we can expect to happen in the future. And I think a few pointers about how we need to do things differently as well in climate science and working more together on these type of topics. So I want us to start with something that happened in 2021. And I think a number of you will remember the German floods. This is really the first time that people, policymakers, decision makers in the UK really sat up and thought about floods and global warming. You can see the very dramatic photo there, a drone flight over the floods of the devastation that was caused by this flood event. Very large amount of rainfall from a cut-off low event. It's caused flash floods in London, went across the Netherlands and Belgium, again caused flash floods, and then hit Germany and just sat there over a large area, huge amounts of rainfall, but a very well forecast event, but one that a rapid attribution study showed had been made more frequent and more intense from global warming. And the reason that people were so horrified in the UK is obviously, you know, whether this sort of thing could happen in the UK. And how do we prepare for this type of event? Now, this event was really well forecast, and that's one thing to say from the outset. You know, 200 people should not have died in this event. It was well forecast, but still many, many people died. It precipitated an inquiry by the Joint Committee on National Security Strategy within the UK. I imagine there was a lot of countries, particularly in Europe, that were thinking about this type of thing at the time as well, in whether we were actually prepared for this type of event and other types of extreme weather as well. And of course, unsurprisingly, I suppose, from my perspective, on the adaptation committee and from the perspective of knowing how we deal with these types of events in the UK, they found that actually we're not prepared, right? The government needs to get a grip, and we need to basically think about prevention rather than reaction to these types of events. And I think particularly, with the rapid climate changes we're seeing, we really need to be thinking about how we prepare for these events more thoroughly. What are the gaps in the research that we need to do to actually understand more about what type of events are possible already, and actually how is climate change going to affect not just these types of very large floods, but also the smaller scale flash floods, actually, that I know that a lot of us are interested in. In terms of global economic risks, this is the report from 2025, and we can see that over a 10-year time period, all of those top risks are environmental. They're based around the climate and the nature crisis, and extreme weather events come out top in terms of a 10-year severity. It's only misinformation and disinformation that comes out above extreme weather events on the short term. And so, and I think that's actually a big problem for us in terms of science, actually, as well. And particularly now, all of the information, that comes out of the US, and all of the ongoing crisis in many governments across the world, that politically climate change is not necessarily popular, but unfortunately the physics doesn't care, the planet doesn't care, and extreme weather is going to continue, regardless of what the politicians think. And of course, Paris was a fantastic international agreement. For the first time, it was agreed that we would try and keep global mean surface temperatures below 2 degrees and really try to keep them below 1.5 degrees of warming. 2024 was the first year above 1.5 degrees following the El Nino event. And then we can see there on the right that almost, every day in 2024 was well above 1 degree warmer than the pre-industrial average. And probably 3/4 of the days were well above 1.5 degrees above the pre-industrial average. And then if we look at the last 3 years, those last 3 years have been the hottest on record. And actually the last 3 years on average are well above 1.5 degrees. So we're basically getting to the state now where if you look at this, these probability, these distributions basically of the daily global mean temperature anomalies from the 1991 to 2020 average, from 1940 up to 2025, you can see those El Nino events stand out there, and they're much warmer than the average. But actually, we haven't returned to a sort of pre-El Nino state, unsurprisingly. We're expecting a super El Nino at the end of this year, and that's looking increasingly likely. And I think we'll know by the end of next month whether this is definitely going to happen or not. But if we do experience that, it's going to be well above 1.5 degrees warmer next year, possibly nearer to 1.7, according to James Hansen. And of course, this matters because the warming atmosphere is directly related to the types of rainfall extremes we get and the intensification of rainfall in the atmosphere, particularly through the Clausius-Clapeyron relationship that we all know about, where we get about a 6.5 to 7% increase in the intensity of rainfall with a 1 degree rise in temperature. And it causes really record-shattering rainfall extremes. And we're seeing more and more of these every year now. This is just an example from summer and autumn 2023. Many of these are associated with big blocked systems now, and you can see there a classic omega block in the bottom left-hand corner with a heat wave over Central Europe, and then two very large cut-off lows either side, and they're called cut-off lows because they've been cut off from the jet stream. So this meandering jet stream has slowed down so much that those low pressure centers have become cut off. And what happens then is they sit in one place for a long period of time, and they cause very, very extreme amounts of rainfall because they just keep taking water from the oceans and dumping it on the land. And you can see that in Greece, Storm Daniel produced over a metre of rainfall in 3 days over a very large area of land. It flooded about a fifth of the agricultural land in Greece, and a similar event in Spain at the same time caused over nearly 250 millimetres of rain in 24 hours, causing massive floods there as well. And then because the Mediterranean was so warm, and again, sea surface temperatures not only drive these events, but also persist these events as well, it went off into the Mediterranean, Storm Daniel. It became a medicane, so it's a hurricane in the Mediterranean, and it hit Libya and caused, I think, over 10,000 deaths there, with a huge record-breaking extreme rainfall event there. And so these were a series of devastating floods around the world from the 3rd to the 10th of September 2023. And what we've seen in recent years is more and more of these blocked wave patterns in both the north and the southern hemisphere, and I'm going to talk about those in this talk, with these slow-moving cut-off lows, which cause very, very large floods across large regions. We've seen intensification, and particularly rapid intensification of tropical cyclones in many locations. We didn't see so many there weren't any major ones that landfell the US last year, but there were still major hurricanes and tropical cyclones in the Philippines. And in particular, we're seeing a huge number now of severe convective storms, and they're causing billions of dollars of damage. And actually last year, the severe convective storms caused many more damages than hurricanes, and they're a big problem for insurance losses now. So not just from flash flooding, but from hail, from lightning, from severe wind gusts and tornadoes as well. And then, of course, if we look at 2024, we saw a similar picture. You can see the same sort of system here causing Storm Boris. Again, if we have a review of the year, we see the same types of extremes. Compound events now becoming commonplace as well, where we get droughts following extreme rainfall, following heat waves, or we get successive storms, and we get cascading impacts as well. And one of the big events as well that happened after Storm Boris in October, the end of October 2024, of course, that really horrific event in Valencia, Spain as well. So 760 millimetres of rainfall in just 24 hours, causing these flash floods in Spain that again killed around 200 people. Last year, we had a nice review recently in the Willis Natural Catastrophe Review, if you're interested. But looking at floods and record-breaking rainfall events and flood events in 2025, and we've got another Nature Reviews Earth and Environment review coming out soon on rainfall side of this as well. The interesting thing is that these record-breaking floods are happening in places I guess we don't expect to necessarily get floods happen, particularly from flash floods. There's a lot more flash floods than there have been historically, and I think this idea that you can get flash floods almost anywhere now is key to what we find when we review what happened last year and what we review in this article. So what I'm going to talk about in this talk is I think the need to think about these events as connected. So what I'm going to argue is that all of these different types of extreme weather events that we see are actually connected through these blocking patterns that we quite often see in the Northern Hemisphere summer. And I would argue that these patterns are becoming more prominent with climate change. as we see an increased warming at the poles, and that reduces the temperature gradient between the equator and the poles, and that's what actually drives the mid-latitude jet. And as we reduce that, it weakens the jet, makes it more meandering, and we get more of these blocking persistent blocks, which cause heat domes, the blocks themselves, and forest fires, of course. We can see this is 2021 summer. You can see that we had obviously the heat dome in the US and obviously over in Russia as well. But it also causes associated cut-off lows and blocked low pressure centers, which cause the Germany floods and the floods in China. And on the edges of both of these, you get these very, very intense rainstorms, which cause flash floods as well, and all sorts of other convective storm events. So it's all connected, and we need to think about these types of systems as connected systems so that we can start to plan for their compounding effects. The other thing that I think we need to do much better in the community, firstly, there was a nice paper out by Hannah Cloak's group at Reading University, just I think, in 2024, about the German floods. So one of the problems with the German floods was not that it was not forecast, it's just simply that people couldn't imagine it being as bad as it was. So people didn't actually evacuate because they couldn't believe that it was going to be that bad. They couldn't imagine that it was going to be that bad, even though they were told that it was going to be that bad. So part of our job as scientists, I think now, is to really think about how we actually transform our scientific information into information that can be taken in by the public and digested and used to try and understand actually the types of events that can happen. Because we really are living in such a rapidly changing climate, we cannot estimate things like the 100-year event anymore. That really needs a lot of data that we don't have. And we need to therefore use other methods, I think, to try to think about what these events might look like and try to educate the public about this imagination and this being able to sort of visualize these events is really, really important in terms of actually preparing for them and making sure that people don't actually, run down to their underground garage and take their cars out and try to drive away during one of these events. The other thing that I think is really interesting that came out recently is a paper by Vavakwa et al. Literally a month or so ago now. Go and have a look at this. It's an unsurprising study to me in the sense that I work in engineering, and perhaps for many of you it will be unsurprising as well. The idea that we need to actually take a risk-based approach to thinking about climate change. But what they argue is actually that we don't at the moment. So at the moment, we very much take we take an ensemble of opportunity from climate models. We take that ensemble and we basically use the multi-model mean most of the time to actually think about planning adaptation or to think about what risks might happen. And actually, that's not a very sensible thing to do. And actually, in IPCC language, a 10% probability is actually low likelihood, right? I can't imagine that many of you would get on a plane if I said to you, well, it's got a 10% probability of crashing today, right? It's not a low likelihood event, actually. It's quite a high likelihood event, particularly if we start to think about the world that we work in when we're thinking about flooding. We design for the 1 in 100 or the 1 in 200 event. Sometimes we design for a 1 in 1,000 event for major dams, or a 1 in 10,000 event even, right? For the coastal dams around the Netherlands. So when we're thinking about these climate change risks, we also need to be thinking about these worst case climate outcomes rather than the multi-model mean. And I think that's a significant change in thinking that we need to take through into our research as well. Maybe some of us already are, but I think that a lot of people aren't. And actually, a lot of the climate allowances and the design criteria that we're actually using at the moment is based on this idea of multi-model means. And so we're almost certainly underestimating the potential for changing risk. So I'll quickly move through some of this because you've probably seen quite a lot of this already, but just to set a context. So I've been working for a number of years on convection permitting climate models, and together with Lizzie Kendon, we We produced the first study on this. We took a weather forecast model, we ran it as a climate model, we forced it with greenhouse gases. And the reason we did this is because convection parameterized climate models, the conventional climate models that we run as regional or global scales, could not tell us anything about what was going to happen to warm season rainfall extremes. And you can see that there. So the 12-kilometre model, the future changes are really uncertain. So white bits show the uncertain sign of change. When we actually run a weather forecast resolution model that can resolve deep convection, we find that actually we see this significant increase in short duration rainfall extremes for the end of the century. And this is what we'd expect from the physics, from the Clausius-Clapeyron relationship. And so this was really a revolution in climate modelling. And it's obviously moved on a lot. So that was, the first studies were sort of 2010 or so. It's now, what, 16 years later. So things have moved on a lot. We've now got a number of different groups around the world that actually run these models. You can see there a European scale simulation that we've run. The good thing about this is we know now that they produce much more realistic rainfall intensities and extremes, durations, etc. But we can also use them to tell us about things like changes to hail and lightning and extreme wind gusts. And we know that they not only produce better representations of these events, but they also produce better simulations of the changes in these events as well, in terms of the scaling with temperature, which really aren't produced by these conventional global climate models. The other thing that we've been doing is collecting together very comprehensive global data sets of observations, rainfall observations at hourly scales. And again, if you're interested, you can have a look through some of these papers. We're updating this data set at the moment with the last 10 years of data. And hopefully we'll be able to actually look at some of the changes that we've seen in observations with these new records, which will be really nice to do. And so what do we know? Well, we know that rainfall extremes around the world are increasing at approximately a Clausius-Clapeyron rate with warming, or much higher rates actually for some of the short duration extremes, and they're intensifying at those rates. We know from lots of groups around the world, not just my group, that the most intense part of the storm is getting more intense and is expected to continue to become more intense with climate change. And we also know that storms become more front-loaded, so more of the rainfall falls in the immediate start of the storm with warming. So you get more of these really intense sudden downbursts with warming. We also know that where there's no moisture restrictions, and that's the UK, there's lots of places in the world where there really aren't any restrictions on moisture availability, where your main source, I suppose, direction of wind comes over a very warm ocean, for example. Storms not only become more intense, but they become larger as well. And one of the things that I've been working on recently with Get Lendering at KNMI is looking at this operational attribution system, where they, for every event they simulate as a forecast, they also produce a past simulation, if you like. So taking away 1.5 degrees, and they also produce a 1.5 degree warmer world as well, and a 3 degree warmer world. And you can use this to see how events might be different. But events that are happening today, or tomorrow, in fact, might be different in a warmer or a pre-industrial world. One of the very scary things about this type of work is it's really shown that rainfall events have the potential to increase at very, very large rates. So the volume of, not just the peak intensity, but the volume of rainfall events quite often increases at a 2 times Clausius-Clapeyron rate, or even higher than that. And we're yet to understand all of the processes behind this, but this is what the weather forecast models are suggesting. So there's the potential with warming for very, very large increases in the volume of rainfall events. So I'm going to return again to this blocked pattern causing persistent weather extremes and try and explain why I think these are connected. So one of the things to say is well, Europe is warming at a much faster rate than much of the rest of the world. There's an increasing frequency and intensity of heat waves, and you can see there in the PDFs the intensity trend over Europe compared to the rest of the mid-latitudes. You can also see that there are hot spots of intensity changes over the eastern seaboard of the US and also over parts of Asia as well. We also know that basically we did some work at about the same time as the German floods, and we know that slow-moving storms are projected to become more common from convection permitting models. So we're looking at something like a 14 times more common over land by the end of the century. So that fits in with what we're already seeing in the real world as well. So we're not just going to see intensity increases, but we also see changes to the movement of storms and storm size. And from observational studies, we know that in parts of the mid-latitudes, and particularly in Central Europe, actually, when we were looking at this, around 40% of heat waves are followed by these short duration extreme downbursts of rainfall. And this is interesting, actually, because it's almost certainly an underestimate of the number of heat waves followed by hourly extreme rainfall, because we're using gauge observations here. And we know that about 85% of hourly rainfall events are not captured by those gauge observations when we've compared them to radar data for Germany and the UK, for example. So that's probably an underestimate. And what I wanted to show you is why that's happening. So I'm kind of showing you this study the other way round. But basically, if we take, and we can do this for Germany, I could have shown you the maps for Germany or for France or for other parts of Europe, but this is for the UK here. What we've done is we've taken the top 20 3-hour rainfall events for the UK over the last 30 years. And we've just taken a composite of what happened on the event day. So for each of those 20 event days, we've taken a composite using ERA 5 of the temperature. And then we've looked at what happens on the lead up to that event and what happens afterwards, right? And what you can see is that in the days leading up to this very intense rainfall event in the UK, this is from observations, the rainfall event itself, from gauge observations, not from ERA. We basically see the buildup of this heat and this blocking heat wave over Scandinavia. And then on the event day, the heat wave peaks. And then you can see as we go into the days after the heat wave, you see these kind of cooling centers. It's a typical omega block pattern, basically, you see there, with the heat wave in the center and then these cooler areas to either side, which probably suggests rainfall and this cooling effect. And what we can also see is that basically we see this composite of the meridional wind anomalies, again, from the same event, same set of 20 events. We wouldn't necessarily expect to see anything from a composite in the larger scale Northern Hemisphere. We wouldn't expect to see a composite across the top 20 UK rainfall events. But actually what we see is very clearly is a Rossby wave, which basically is a quasi-stationary wave in the atmosphere. And it causes this blocking, this heat wave. And as it then catches up, eventually, you see this event day happen. So that's the day that the rainfall event happens, and then after that you see the wave breaks, the heat wave dissipates, and everything disappears. But what we can see in the top right-hand corner there is what we think is happening during this event. So we've got this omega block, and we've got these cut-off lows either side of it, which we're calling a Rex vortex here, because that's what they call them in meteorology rather than climate science. So we have different names for things as well. Basically what happens is you get this, this warm air advection towards the wrecks between the cutoff low and the omega block. And that basically causes these layers to be created that are very conditionally unstable. And that causes these extreme downpours at the edges of these systems as well, but also causes lightning and also causes hail as well. And that's explained in this paper by Davies et al. If you're interested in terms of this new conceptual model for how these events happen. But what that means is that we're, as heat waves increase in Europe and in other parts of the world, we're potentially going to see more and more of these events. So we see these big heat events, we see these big cut-off low events with massive, very, very large-scale flooding, but we also see flash floods as well on the edge of these systems. And it suggests that all of these things are compounding and connected and all increasing with climate change. And if we look at these things separately from convection permitting models, we see that this is looking at changes in lightning over Europe. You can see that we see quite significant changes in increases rather in lightning over southern Europe in the autumn, over northern Europe in the winter, over the sea, and also over the summer over the land. And we also see that the models suggest that that hail will, in general, the frequency of hail will reduce because of the melting level increases, but actually it will increase the biggest hail in Europe. So, this all fits. I mean, one of the really interesting questions that we would like to ask is, what happens to these compound extremes in these storms? What types of storms produce hail? What types of storms produce lightning? And the rainfall side of things, and are these more or less predictable and more or less frequent in a warmer world? So I'm quickly going to talk about changes to precipitation as well in the winter before I move on to think a little bit about why we should be cautious about climate models. So one thing that one of my PhD students, now postdocs, has looked at in the last year or so is changes to winter precipitation in Northern Europe, and this is using observations. So he's basically estimated how much rainfall we would expect to occur for the UK and for other parts of Northern Europe for each particular pattern from a set of 30 synoptic weather patterns. And then he's taken that estimated amount away from the actual observed winter precipitation. And this just shows the results for the UK. But you can see that when you actually take those away from each other, the second row there shows you the difference. And you can see that from the 1980s or so, you start to see this significant difference, which can be represented by a trend. And that trend is actually consistent with a 7% increase in mean winter precipitation across the whole of the UK in this case, but the whole of Northern Europe actually, per degree of warming since 1980, which is attributable to human-induced global warming. And that means that we've seen a huge increase in precipitation in the winter from this increase in temperature. And that's consistent with what we've seen in terms of observed regional trends in river flood discharges as well, particularly these increases in Northern Europe and the reductions in the south. We're also seeing significant reductions in winter rainfall in the south of Europe as well, associated with the same warming signal. This is really important, I think, for flooding in the winter because it just increases the saturation of the ground and the antecedent moisture conditions, and means that when smaller rainfall events can actually cause big floods because we already have very saturated conditions. So quickly, I want to say something about climate models, because I think there's some problems with climate models that means we need to be a bit cautious when we use their outputs, and we shouldn't just be using them blindly to explore changes to floods. One of the issues with climate models is that they are underestimating the changes in heat extremes. And this matters because of those connections to the rainfall extremes that I've already talked about previously in the talk. And in particular, this is a nice paper by Robert Vortard et al. You can see there that they split up these changes into those coming from the dynamics, changes in the sort of large scale atmosphere, and those coming from changes in the temperature, the mean temperature itself. And you can see they've compared that to two observed data sets. All of the CMIP6 models in that dynamical trend plot A there, underestimate what we're seeing in observations. And most of the models also underestimate the warming trend as well. But basically, it's suggesting we're not getting the atmospheric dynamics right, or the changes in the atmospheric dynamics right. And that's why we're not getting these trends in heat waves. And that's because I think that climate models underestimate the persistence of these long-lived blocks, these high pressure episodes. And the unfortunate thing about this, and this shows some results for winter, that it's the same for summer, that actually as we get to higher and higher resolution models, certainly as we get to 25-kilometer resolution global climate models, which is about the sort of state of the art now, unless we look at things like Destination Earth, then we're not really getting an improvement in the persistence of these blocks from the climate models. And the other issue is that climate models are also underestimating the rate at which winter precipitation is increasing with temperature. And again, this is showing the results for the UK, but this is true across Northern Europe. If we look at observations and the changes in observations on the red line there, you can see, and then we look at the CMIP6 global climate models, you can see that the global climate models aren't predicting the observed changes that we're already seeing in winter rainfall until about the 2040s. And this matters because actually we're seeing about 3 million Olympic-sized swimming pools of extra water every year in the UK, and that's the same across Northern Europe. The good news is that most of the convection permitting models seem to produce a reasonable estimate of the scaling that we're seeing, or the change, the increase in winter rainfall with temperature, but regional climate models and global climate models don't do this. So we've got to be really careful if we're using these to give us projections of changes to rainfall, because they're underestimating the rate of change. So what I'm moving on to doing next, or I suppose I'm doing this already actually, so I've now got a Faraday Discovery Fellowship from the Royal Society. I think that, what we're going to be trying to do in this, it's a 10-year fellowship, and working with a big group of people in the UK and around the world, is to actually connect weather and climate together. So really thinking about how does climate variability drive weather extremes around the world, and then thinking about how climate change moderates that on top of the climate variability. So really thinking about things in a very different way to the way they're thought about at the moment. And we're going to try to improve forecasts up from seasonal up to multi-annual scales. We're also going to try and improve the projections of extreme weather, and to also monitor changing risks as well. And part of this is going to be about developing storylines as well. And I'm using one of Ted Shepard's diagrams here. So this is a diagram from his paper in 2019, and I want to change this because within this diagram, he's not thinking about natural modes of variability. So that's a big missing one for me, and that really drives extreme weather. And then the other thing is that we're thinking about events rather than individual hazards. So because these things are connected in space and time, we're thinking about events, and we're thinking about how drivers, including natural modes of variability, actually cause regimes, and they cause events. And we think that these things are predictable. So it'd be interesting to see how we get on with this. Part of this again is about producing storylines. And the nice thing about storylines is we can actually incorporate information from different types of models, from observations, from our seamless framework as well, and from climate models, through a sort of quantitative. I think we're going to, at the moment it's quite qualitative, but we're going to produce a much more quantitative conditional framework for this as well within the fellowship. Just before I finish, I thought a thought exercise on how extreme rainfall can get would be interesting. This is just for the UK, but really thinking through some of those events that have happened already. Mostly they've received up to 2/3 of their annual average rainfall in 3 or 4 days, sometimes more than the annual average rainfall in 24 hours. If we start to think about what might be plausible in the UK through some of the physics and thinking, I think an event of about 400 millimeters in London over 3 or 4 days is already possible within what we've seen. It could be bigger than this in other parts of the UK. And actually in the paper with Get Lender Inc., where we look at the operational attribution, hourly extremes can actually intensify by up to 21% per degree C. And whole event volume can increase by 7 to 14%. So as we get a warmer climate, we can add very much to those quite crazy totals that I would argue are already possible, actually, and certainly have already happened in parts of Europe already. So final slide here, and I think you've all got the gist of this already, but we need to be thinking about global to local drivers. We need to be thinking about the integration between multi-hazards. And it's really crucial that we start to think and work together much more now for adaptation decisions. We have to be very careful about how we use climate models. I'm not saying we should stop using climate models, right? Because they are the only game in town for thinking about the future. But we need to be very careful about using their outputs, and we need to really think about whether they're underestimating potential changes in risk. They might be overestimating it too, right? But we need to be careful about using the outputs and not just use them blindly. And if you're interested in actually looking at this type of thing, then there's a very nice book that we published last year with Linda Mearns, who sadly passed away before the book was published, but she led this amazing book on uncertainty and climate change research. And one of her key messages was that this uncertainty should not stop action, that we need to act with uncertainty, was one of the key things she always said. And actually, we need to basically enable science to support robust decision making now, because certainly with the super El Nino that's going to happen this year, we're going to need more and more to be thinking about adaptation as well as net zero planning. Thanks very much.
Thank you, Hayley. Great presentation. Wonderful. Yes, thank you. Great job. Any question you guys may have for Professor Hayley?
Hey, Haley. This is Josh. Yeah, really great presentation. Really enjoyed it. It's a great work that you're doing. So I really appreciate you taking the time to share that with us. One thing I was thinking about when you were talking about those blocking highs and the wave train coming across, right? Have you thought much? You seem to talk about it as like a lack in the climate models to be able to get the atmospheric dynamics. How much have you thought about also the land feedbacks, particularly part of the stuff I work on is like relative to like vegetation, and like the way they treat vegetation in these models is just not really accurate, just assuming it's always climatological or whatever.
Yeah, interestingly, I was talking to one of my PhD students about this morning because he's looking at wildfires. And I think that one of the reasons that we're seeing it's not just about the atmosphere, absolutely, right? One, it's about the ocean and the feedbacks from the ocean and the extra heat from the ocean sort of amplifying these effects. But it's also about the land surface feedbacks. And yeah, I think it's hydrology, right? So we need proper hydrology in land surface schemes in climate models. we need to be able to represent soil moisture processes better. We need to represent the vegetation better as well. And of course, Daniel Swain produced that really nice paper on hydroclimate whiplash, right? But the reason that we're getting this whiplash events is partly because of the atmosphere and the increased blocking and these rapid transitions, but it's also to do with the amplification from, we get these really wet periods, lots of vegetation grows, right? And then we get these really hot periods, and you get all of this extra evaporation from the land, from the vegetation and everything, and it amplifies that heating as well. So I don't know, it's really interesting, and I think that one of the reasons that the blocking events don't stay in one place, persist, sorry, for long enough in the climate models is actually because of the lack of land surface feedbacks. And I mean, Sonia Sinovaratni showed that really well for the 2003 event. I don't know if you've ever come across her papers, but it was a long time ago now, but she did some really nice work just looking at the effect of using different land surface schemes on the persistence of that event. And you couldn't reproduce that event well in climate models unless you actually treated the land surface more, in a more realistic way. So I think you're absolutely right. I think that the land surface processes are really key. Once we get to these sort of convection permitting scales and to very high resolutions, you need more and more of that in there. So it's something that really needs to be thought about. Climate scientists almost exclusively concentrate on the atmosphere, and actually the atmosphere is by, the ocean is the driver, right? And then the land surface is the moderator.
Yeah, no, I agree. And I guess I'm also curious, do you think like our biggest lack in this area is data or sophisticated models?
Oh, that's a good question. I think there's going to be a continual lack of data, actually. I mean, I think the models are obviously an issue. So there are processes that we don't even necessarily know about that are probably missing from models, right? There are some processes that aren't well represented in models, like hydrology, right? We don't even have lateral flow between grid cells in models, right, for the hydrology. But there's also a problem with observations as well, because there's many parts of the world that aren't well observed, particularly for precipitation. Satellite data to a certain extent is solving some of that, but still has massive biases. And then there's at the moment there's massive de-investments or whatever in observational science, I think, across the US, but also happening in the UK as well. People think that they even got rid of the aircraft that they used to run campaigns with in the UK now, thinking that we can use drones instead. But we're not going to be able to use drones for many of these things, right? You can't imagine a drone flying into a big storm or something like that. It's just not going to happen. So I think it's a bit of both, really. But it's key with the rapid climate change that we're experiencing at the moment. It's really key that we keep the observational science going, because we need to be able to see where these changes are happening and fast. And I don't think we can constrain our models unless we actually understand what's happening in the real world either. So it's really important to do both. I am hopeful that kilometre resolution models will solve some of these issues, and they do appear to solve some of them from the sort of short runs that have been done so far with things like Destination Earth, but it won't resolve everything.
No.
So it's how do we make decisions with imperfect information, because we can't wait until the climate models give us the answer, because they're never going to, right? And we've been naive to think they will, I think, well, maybe people don't care really, but I care.
Yeah, no, I agree.
Society, I think, we put things off until we're certain about something, and we're never going to be certain about something, but we certainly know what trajectory we're going in and the type of things that are possible now, never mind what might be plausible in the future.
Yeah, no, I agree. This is great. I appreciate your response to all that. I think it's an awesome perspective, and keep doing the great work that you are. It's awesome.
Thanks.
Thank you, Josh. Any other question you guys may have?
May I?
Yes.
Okay.
Yes, please go ahead.
Thank you for Dr. Haley for her presentation. Great presentation. My name is Arvin, and actually I have a question. How do change in atmospheric moisture and the land-scale weather pattern work together to decide if future rainstorm will get more intense at their peak or effect on the, uh, spread out over a larger scale? I mean, it's
So what, sorry, the atmospheric moisture and what else?
you talk about the atmosphere moisture and the larger scale weather pattern work together, okay? To decide that if a future rainstorm will get more intense at their peak. Okay, my question is that is it affect more on their future peak or the scale?
So, if there is a limitation in atmospheric moisture, so say you're looking at, I don't know, Central Europe, right? Or some kind of continental location, you will still get, with warmer temperatures, you still get an intensification of the peak rainfall in the storm, right? So you get a Clausius-Clapeyron scaling, or even higher than Clausius-Clapeyron scaling still in that peak. If you imagine a storm as kind of like a three-dimensional object with a peak in the center, right? It's very theoretical. But you get this peak in the center that becomes more intense, whether you're in a moisture limited or a moisture available climate. But the difference is that because you've got limited moisture available, as you converge that storm and you get more intense uplifts and more intense processes going on, it intensifies the core, but it reduces the size of the storm because more of that moisture is concentrated into the actual core of the storm, if you like, right? So that would be in, say, a continental climate. Whereas in a climate where you don't have any type of moisture availability restrictions or limitations, you can just keep converging moisture into that storm, right? So you increase the intensity at the center, but you also increase the intensity and the size of the storm throughout the storm as well. And then if you also have basically the storm slowing down or becoming stationary, you have big problems, right? Because you have a bigger storm, you have more intense rainfall anyway, but you also have a storm that sits in the same place for a really long time. So it just dumps huge amounts of moisture in one place. I don't know if that answers your question.
Okay. Yeah, thank you so much.
Yeah.
Thank you. Any other question you guys may have? Yes, Bernard, if you could ask it very quick, that would be great.
Yeah, thank you very much. Good morning, good afternoon, and thanks, Prof, for a very good presentation. I've really enjoyed your presentation. On one hand, we see the extremes in both extreme rainfalls and also temperatures increasing. On the other hand, there has been a dedicated advocacy around the reduction of greenhouse emissions into the atmosphere that would otherwise accelerate the global warming. Yet we continue to see this. A lot of investment has been done to control emissions, but at the same time, we continue seeing extreme events. Can we say that perhaps the approach to climate change or other emissions reduction or mitigation is perhaps we are missing something, or the extremes that we are experiencing today are caused by the past emissions that we have no control over?
Oh yeah.
Thank you.
So I mean, basically, the weather extremes are caused by they're caused by lots of things, right? They're caused by natural cycles, and then on top of that, climate change and climate warming, and that anthropogenic warming is caused by the level of carbon dioxide and other greenhouse gases, fossil fuels, basically, that we put into the atmosphere. And there have been reductions in the increase, the year-on-year increase in fossil fuels. So I think last year we only saw, what, a 2% increase or something like that. But we're still seeing increases every year. China has peaked, I think, but other countries haven't. And so we're until we actually stop putting fossil fuels into the atmosphere, we're going to see increases in extreme weather events, because the warming that we experience globally is linearly related to the concentration of carbon dioxide and other greenhouse gases in the atmosphere. And absolutely right, because there's such a long life for those gases in the atmosphere as well. Even when we stop, it's going to, continue. Extreme events are going to continue to happen beyond that kind of peak carbon dioxide concentration. I mean, we've got nowhere near yet actually reducing these greenhouse gas emissions into to what we said we were going to do with the Paris Agreement, right? We need to peak the amount of greenhouse gases we're actually emitting and then reduce them year on year, and we still haven't reached that peak yet. So I don't think people realise, actually, and this is something that I said at the National Emergency Briefing that we held last year in London, but these are the least extreme weather events you'll probably experience in your lifetime, right? Because warming is going to continue till at least 2050, and with the sort of gases we've already put into the atmosphere, and it will almost certainly continue beyond that, because we're not going to suddenly stop putting greenhouse gases into the atmosphere next year. It'd be lovely if we did, but if we actually rapidly solve the problem, but we're not going to politically. Extreme weather events are going to continue to get worse. So we are, very unlikely that we will, that this is going to be the least extreme climate we will experience our lifetimes. That's a terrifying thought, isn't it?
Yeah, thanks very much. Quite elaborate on that. You talked about the climate models as well. I know that we are using a lot of global climate models, but at local scales, these models are constrained. Is there a way or proposal that are being advanced in trying to see that localized extremes are also captured in the climate models?
So, I mean, they're not. So the localized extremes, like the thunderstorms and hail and all of those type of things, aren't captured in the global climate models until you get to these convection permitting scales, which would be a sort of 2 kilometer, maybe a 4 kilometer scale, right? Maximum. So they're absolutely not simulated. And not only that, they underestimate the rate of change as well in even the large scale rainfall, the sort of larger scale rainfall extremes that you might say get over a day, or you might get in the winter or the cold seasons. They underestimate the changes in those as well.
Great.
Thank you very much.
Yes, thank you. Thank you all. And thank you, Hayley, for the insightful and inspiring keynote. We truly appreciate you sharing your expertise with us. So those of you who follows us every month, next month we will have Professor Stephen Collett as our keynote speaker on June 5th. I hope you guys can join us and make that meeting as well. So thank you again for your participation, and thank you, Hayley, again for your awesome presentations. And I wish you guys a great weekend. Thank you.